Hello and welcome to part 2 of the series of portfolio theory with matrix algebra using Python. In this part I'm going over optimization of portfolio weights and also challenge this optimization using the concepts from the last video. It is therefore very important that you have watched part 1 of the series, otherwise it might be hard to follow along. Important disclaimer, concepts shown in this video are not an investment advice. Video is for educational and entertainment purposes only. Alright, let's get started. We need Y Finance to get asset prices from the internet, NumPy for calculation purposes, pandas for data handling, and from SciPy Optimize I'm importing minimize, which is a function finding the minimum of a given function using a particular solver. Then we are setting up a list of assets, and as in the last video, we are working with the S&P 500 and gold. Pulling prices for those assets using YF download, starting in the beginning of 2010 and only considering the adjusted close column. Then calculate log returns, nothing new until here, right? And with that we have log returns, daily log returns for both assets from 2010 until today or the last trading day. So if you want to see the development, you can just accumulate the log returns. So accumulate the sum of the log return and then plot it. And now you have the development of both assets. We also set up the weights vector, and initially we're just assuming that we have equal weights. So we have a portfolio out of 50% gold and 50% S&P 500. And we're using the exact same syntax as in the last video, where I explained what exactly this is doing. So with that, we have our weights vector, so 50% one asset, 50% the other asset. Next, we need a function which we can actually minimize. Now, what is our goal? We want to find the portfolio with the highest Sharpe ratio, so the highest risk-adjusted return. As we can only minimize, we need to create a function which is calculating the Sharpe ratio, but it's just outputting the number in a negative way, right? So and with that, we can simply find the lowest Sharpe ratio, which is actually the highest Sharpe ratio. So let's call that function Sharpe portfolio. This is taking a weights vector as an argument and also a return data frame. I'm just calling that returns here. First of all, the hardest part probably is calculating the portfolio risk. I've explained that in the last video in detail. So you're just taking the weights vector, take the dot product with the covariance matrix of the return data frame, and then again take the dot product with the weights vector. And finally, you are taking the square root out of that. And with that, you have your portfolio risk or portfolio standard deviation. Now you just need the expected return of the portfolio, which is the weights vector dot product and the mean of the returns. So I'm just creating the Sharpe ratio here, which is simply the expected return. So the weights vector dot product with the average return or the expected return, and then divided by the portfolio risk. So this part is expected return. And finally, as I said, we need it as a negative value as we want to minimize it. So I'm just returning the Sharpe ratio with a negative sign here. So if we take the Sharpe ratio, or if we want to know the Sharpe ratio of an equal weighted portfolio, we're just passing our equal weights or equal weighted vector here, so 0.5 and 0.5, and our return data frame, and with that you get the Sharpe ratio. So of course the Sharpe ratio would be positive if you calculate it the normal way, but as we provide it negatively, you're getting it negatively here. So this is our Sharpe ratio of an equal weighted portfolio. Now the question is, is the equal weighted portfolio the best choice? And this is something we want to answer minimizing this function here. So we want to have the weights combination minimizing the Sharpe ratio here. This is what we are doing. Before just passing this function to the solver, we need to define a constraint. Why? Because we don't need just any combination of weights, but we need a combination of weights which is summing up to 1. Why? Because we can only weight the assets so that we have 100%, right? So this is why we need a constraint. So I'm going to define that as const and provide a type of a constraint. And there are basically two types, an equality constraint and an inequality constraint. The equality constraint means that the constraint function result is to be 0. So I'm using that. So I'm taking equality constraint and then pass a function which is simply taking the sum of the weights. So in this case, just 0.5 plus 0.5, which is 1, and then subtracts the 1. And with that, I should always get a 0, right? So whenever this the sum of this vector is 1, this constraint is fulfilled. So this is our constraint for the minimization here. And next we can simply minimize. So I'm calling the minimize function, which I've imported above, pass the function I want to minimize, so the Sharpe portfolio function, pass our initial guess. So our initial guess is just equal weights here, right? Then I need the parameters of the function, which is my return data frame, and I also need to pass my constraints, which is one constraint here, that the weights summing up to 1. Running this, I'm getting this output, and the suggested weights are 33% and 67%, right? So it not recommends, but it is telling me that overweighting the S&P 500 is a good idea in terms of minimizing the Sharpe ratio, or rather maximizing the Sharpe ratio, right? So let's store that somewhere. So optimal weights, and I'm simply, let's store that in results here, res, and I'm just storing the array here. So res x, and with that I have a vector of optimal weights here. All right. So if we are taking a look, for instance, how the portfolio would have developed, we could just take the return data frame and take the dot product with the optimal weights and then accumulate it. And then you see the portfolio would have performed quite nicely. You can compare that to the equal weights portfolio, and you see that the optimal weighted portfolio is outperforming the equal weighted portfolio. All right. So of course, right now we are passing the whole data set, right? We are splitting the data set and see what is happening then in some seconds. But before doing so, I want to show you that you can do the minimization for yourself. It's important to understand that what I'm doing is not exactly what this minimization function is doing. I just want to show you that you can use an iterative approach to also get the minimum. How can you do that? You can just fire some parameters to the Sharpe ratio or the Sharpe portfolio function, and then see what combination of parameters, or rather weights, is minimizing this function. I will show you that because I think it's helpful to understand how an iterative approach would look like if you, let's say, don't trust these solver functions. So what you can do is simply create an array of values. So let's say 0 to 1, and then with step sizes 0.01. And with that, you're getting an array like this. So we are starting with 0, then 0.01. So you have a weight for the first asset, and you're getting the weight for the second asset if you're just subtracting 1 from, or other way around, if you are subtracting the array from 1. Right, and then you're just getting the counterweight. And you can just loop over that and fire that to the Sharpe Ratio function. So you would do it something like that. You're just storing the Sharpe Ratio somewhere, and then for weight in this array, then you're defining the weights as simply W and 1 minus W explained here. So weight and counterweight. Then you're creating an array out of that. And then let's print out the weights so you see what is happening in each iteration here. And then you're just appending to the sharps list here and call the function, right? So Sharpe portfolio, pass the weights, and take the return data frame. So if you're executing that, you see that in the first iteration, you have 0% of one and first asset and 100% of second asset, 1%, 99%, 2%, 98%, and so on, right? And this should end up the same as the minimization function, at least roughly the same, right? Because we're taking 0.01 steps here. So let's find out. So I'm using a series for the sharps and then plot it, because that is quite interesting how this is looking like. So you see this curve here, and somewhere here is the minimum of Sharpe ratio. After that, it only gets worse, right? So if you want to find the minimum here, I'm just taking n smallest. You see that at iteration, it has the lowest Sharpe ratio. At iteration 33, it has the lowest Sharpe ratio. So you can just check where that is. And you see, which makes sense, you could have done that in your head also. You see that the first asset should be weighted 0.33. And what does our minimization function is telling us? 0.33, right? So this is the iterative way to find that out. But again, this is not exactly what the solver is doing, right? You will need some more effort to mirror what exactly the solver is doing. If you're interested in that, let me know, but this should help you understand how an iterative approach could look like. Okay, now we're getting to the interesting question. We fed all the data set into the optimization, right? What is happening if we split the data set, optimize it on a particular share of the data set, and then see how the portfolio would have performed, both in terms of performance in general, so return, but also in terms of Sharpe ratio. So let's scroll a bit down here and define a train data set. So this is simply taking our return data frame, and now I'm just taking 70% of the return data frame. So I'm taking reddf, the length of reddf, which is the number of rows times 70, so just 70% of the length of the return data frame. So this is simply the number of rows times 0.7, and then I'm just rounding it, right? Because this is not something you can use to split the data set, so I'm just doing an integer rounding here. So I'm taking the integer of this number coming up, and then I'm just saying, okay, give me all the data until this number. Okay, and with that, I'm getting my train set. So starting in the beginning of 2010 and going until somewhere in February 2019. And same logic for the test set. So I'm just basically copy pasting this and then say go from there on. And with that, I'm getting all data from the February date on until today or the last trading day. Alright, so now I have a train set and a test set, and I'm doing the optimization on the train set. So let's do that. Let's store that in results train, call our minimize function, use our Sharpe Ratio function, our initial weights as, our equal weights as the initial gas, and then our train set here, and also pass that our weights must sum up to 1. With that, we are getting different weights, as you see, right? And now you could see how the portfolio would have performed if you're just taking those weights from somewhere February on, right? So how can you do that? You're just taking the test set and take the dot product with this weights vector. So I'm just taking X here and then accumulate the returns, and that would be your performance. So how would it look like if you take the equal weighted portfolio? Just take the dot product with the equal weighted vector, then take the cumulative sum. So a slightly better performance, right? But not a big difference, as you see. So you could also compare the Sharpe ratio. That is the far more interesting part. So you're just passing the optimized weights on the training data set and take the test data set where you are calculating the Sharpe ratio on, right? So you're just taking the covariance matrix of the test data set and the expected return of the test data set here with the weights on the trained on the training data set. And you're getting a Sharpe ratio of 2.9. So if you compare that with the equal weights, just copy pasting that here, so I'm just passing the equal weights, you're interestingly getting a higher Sharpe ratio on an equal weighted portfolio, right? And this shows that considering unseen data is an important thing here, right? But this is only for a 2-asset case. What is happening if you add some assets here? So let's add an asset. For instance, let's add Tesla 3M, and let's just run it again. So Tesla clearly outperformed all. So now you have 25% of the weights, right? Sharpe ratio of an equal weight portfolio is this. Run the optimization on the full data set. You're getting those weights. And this is an interesting thing now. You're getting a negative weight, and it's good that I covered it in this video. It actually wasn't my intention to go that far in this video, but this is also an important point. It depends on your preference. Do you want to allow short selling? So this is indicating that you are negatively weighting that. But I would prevent negative weights here. And you can actually just do that by defining bounds in your optimization. So to avoid negative weights, you could just define bounds here. You have to actually import them first because it's easier. So from Sharpe optimize bounds, and then you can just pass bounds here and then define bounds 0 to 1. So with that, you will see that I don't have negative weights here anymore. So my optimal weights are looking like this. I can take a look at the portfolio performance with the optimized weights. Then with the equal weights are outperforming the optimized weights. Very interesting here on the whole data set. So if we are doing the train test split and do the optimization again, of course, with the bounds here again, we're getting those weights. Now let's compare them. So this is with the optimized on the training set, the portfolio performance. And this is just taking equal weights, and you see that the equal weighted portfolio still outperforms the optimized portfolio. Sharpe ratio wise, also equal weights outperform portfolio. Right? Let's add some more stuff here. Caterpillar, Apple, maybe brand, some commodity here, and run this again. So now we have this as equal weights. Sharpe ratio is this. Optimized weights, this. Comparison is that now the optimized is clearly outperforming the equal weighted portfolio. But now let's do the real thing using train and test. And finally, I got an example where I can show you that the optimized portfolio is outperforming the equal weighted portfolio. Also in terms of Sharpe ratio, no. So equal weights, at least at first hand, hard to outperform here, but it is of course dependent on the assets, right? Anyway, I hope this was interesting. So you can of course take assets which are not correlated with each other, right? So you can play around with a bunch of I don't know, negatively correlated assets and see how you're getting the best Sharpe ratio doing the train test split. But you saw that it is important to consider unseen data, because if you are just considering this alone, right, you would think, wow, optimization of weights is a big thing here, right? But if you consider it using the train test split, you see that it's actually not that easy in the first place to outperform an equal weighted portfolio, right? Of course, just a scratch on the surface, but I think this video was quite interesting. So what can you do from here on? You can actually find assets which are contributing to a better Sharpe ratio using this train test split. That is also a very interesting thing to test. For now, that's it. Thanks a lot for watching. If you have any questions, let me know in the comments below. And yeah, I'm looking forward to see you in the upcoming videos. Bye bye.